Shall I start? Yeah. Welcome. Happy to see that the room is becoming a bit more crowded. This is the IADOPT working group, which already exists now 1 year, but unofficially we are already working for 3 years together, I think. 2 years. We started 2018. And this is now our second ordinary working session at RDA. And today we will have several speakers here. Pierluigi Buttigieg will start with a short introduction to IADOPT activities in the context of other initiatives related to observable properties. Then Alison Bamman will continue describing the outcome of our third task, which is derive use case requirements. And then Gwen Moncoiffé will continue and will present the deliverable 1, which is the catalog of domain-specific terminologies in use in environmental research. And lastly, Maria Stoika will present the outcome of task 4, which is the analysis of semantic representations of observable properties against requirements. I must say that this is not yet completed, this task, so she can just present what we have achieved so far. And then we will have a 40 minutes discussion session introduced by me, where we also will ask some questions to the audience, and at the end 5 minutes wrap up by Gwen. So I think I can stop sharing my screen and I give over to Alison. Thank you very much.
It should be Pierre.
Sorry, it is Pierluigi starting. I am sorry.
That's okay. So hi all, I'll give a little bit of an overview about some of the, let's say, international context and, let's say, digital ecosystem engineering that's happening right now that would very much benefit, or is in a sense already benefiting from IADOPT's work, coordinating all of these different ways of representing parameters. I mean, as we know, parameters are the lifeblood of scientific data. People like to talk about what they measure, how they measure it, which units they use. You know, we obsess about these things quite a bit. But the problem is, because it's such a prominent focus, everyone has their own bearing on it. They have their own system to do it. And it seems to be a lost cause in many ways to try to choose one vocabulary to do it, because it's never complete. And that's what's exciting about IADOPT, in the sense that it won't be complete, but if we align the standards and interoperation solutions, ontologies, terminologies, vocabularies, thesauri, if they're aligned to a common framework that can itself interoperate, we're making life easy across multiple communities that will not talk to each other in a natural way and who cannot usually overlap their development. So it's in that spirit that I'm just going to mention a few of many whose international initiatives, whose thinking is aligning towards IADOPT, let's say, patterns, and which can really leverage the work done in this group. So I'll start close to home. So I'm with the Helmholtz Metadata Collaboration, which is nested within the Helmholtz Data Federation. It's a new sort of platform across the Helmholtz institutes. There are many institutes that are Helmholtz, and they cluster along those hubs or research themes that you see on the left-hand side there: energy, earth and environment, health, aeronautics, matter, key technologies. It's a relatively small national, but when I say small, I mean 40,000 employees and about 5 billion euros a year. But when we're talking about global integration of data, this is a microcosm of a federated system that has a need to integrate parameter descriptions across very different fields whose practitioners typically don't talk to each other. Within the HDF, there is a platform called the Helmholtz Metadata Collaboration, the HMC. And in this, the goals is to keep the data in the system alive. When we publish our papers and we publish our data sets, again, in many cases, a few years down the line, nobody's reading your paper anymore. But if your data is interoperable, it can be used time and time again down history. So that's really the real legacy of scientific activity, of research activity. So it's a high priority to try to keep that alive somehow. And that doesn't mean keep it inside a central storage system. Databases come and go, things are funded and they're defunded. So the main thing is that the data itself, if it's interoperable and portable across different systems, that's what will keep it alive. I am reminded of the case indeed when the US stores of climate data came under threat because of government policies. Very quickly, this was moved over to Europe, European servers, just to keep it safe. Indeed, that's a question of dumping data, but in a sense, once we harmonize that data and build that sort of strategy into our infrastructures, that they can port data to one another just in case something happens, and that can be anything from policy changes to natural disasters, we can keep research flowing. And that's indeed the objective there. Part of that, this is just spun up. The hiring is almost complete. And indeed, this strategy is going to unify multiple institutes and large research activities in an international context. But one thing that's very much in focus is a centralized metadata catalog, which has semantic technologies built into it so that, again, machines understand what the metadata, or data in that case, in some cases, depends on who you are, what it is about, and how to find it through semantic networks. Indeed, building this from scratch is, in a sense, a terrible idea, since a lot of standards and tools are already in operation, but which one do you choose? You can't really make that decision because many of them are used by one community and not another, one hub and not another. And in that case, this is where we're really looking towards IADOPT to say, all right, if you can't choose one solution, at least let the solutions themselves harmonize and talk across one another. Of course, parameters will be a focus, and we are looking towards that framework to help us to reduce the overhead for the HMC. Again, if there's an international rallying point, an international focal point, and convergence point, this is going to help so many national initiatives build towards it. And I think it's a good microcosm for what we're going to face globally. And that sort of takes me to my next example of something a little bit more, well, quite a lot more global. A project, again, that I'll be coordinating the technical work packages on, the Intergovernmental Oceanographic Commission's Ocean Data and Information System, ODIS. So this is being set up, and we've finished regional consultations with the oceanographic regions of the world, and also thematic meetings. We just finished the last of our 6 thematic meetings on key data types to be exchanged across the United Nations, national member states and their national data hubs, as well as anyone who wants to participate inside ocean data science. And ODIS is going to be a system built from many components, each one independent with its own priorities, with its own funding realities, but somehow we need this data to flow from one party to another, at least a minimal subset of it. And so the idea is to use linked data technologies in order to enable this, to plug in UNESCO or UN services that will be providing things like documents, ocean best practices, people, biogeographic information or biodiversity information, oceanography, and combine it with regional stakeholders. These are just a few of the ones who are founding members of the ODIS system. Many more are joining in from the Pacific and others, and it's an open process, who can all project and pull data from a linked data universe. And then the idea here is that people can spin up global hubs. There doesn't need to be a central point that you have to learn how to use because there's interoperability at the heart of it. But again, in order for this to work, the individual components also have to be interoperable. And we must accept that people are going to use multiple ways of describing their metadata. But if it's done in a predictable way, there's some hope of building bridges across regions and eventually converging into a fully interoperational system. It's a tall order, but we have to start somewhere. And I'm quite looking forward to working with this in the UN context because, again, the technology is there. We all know how to build these things. That's not the hard part. There's a diplomatic layer that's needed. There's a negotiation layer that's needed to harmonize how people work, how they compete, and how they collaborate. The ideal solution is that competition is natural. That's how things work in funding cycles, etc. But whatever we leave behind, whatever we build through that competition should be collaborative. It should work together. We should be building something larger if we want to solve some of the grand challenges before us. And again, linked data is the way. Rather than having any one person run it, the web itself is the hub of this system. And we will be using semantic technologies to push and pull data about a number of things through the system. Of course, then, key parameters like the essential ocean variables will be featured here. And once again, understanding how to orient the existing parameter terminologies and knowledge representation technologies will be key. So again, we are tuned in there to the iAdopt activities to make sure that we can scale this and also be inclusive and not turn anyone away. If there are good ideas, it should interoperate with other ideas in the system. We are also consulting with local and indigenous groups and their understandings of data, information, and knowledge, and seeing how we can also coordinate with that, again, to be as inclusive as possible. The long-term goal of that is to build a digital ecosystem for the oceans over here, and merge that with other digital ecosystems that are emerging from partners such as the WMO or city governments, etc., to be able to interoperate and weave together a kind of digital biosphere, which we will need to answer some of these large questions linked to sustainable development. When we talk about things like healthy oceans or mariculture or resilient food systems, we need to push and pull data across all of these different ecosystems. Nothing is in isolation. And this is where neutral ground, good suggestions that are scalable frameworks can be applied and essentially scaled across these groups. So again, we're looking forward to the concepts and the way that this group in particular has got together former competitors into a collaborative framework, very much in the spirit of the digital diplomacy that's needed for the rest of the century. One example in this, just an example of that, this ocean best practices system that's part or that will feed into ODIS. It's one of those things that will take any document. So it doesn't just have to be raw data or annotations. Any documents uploaded into the system get natural language processed, text mined against a set of ontologies and vocabularies to be able to do sort of federated search and plug into ODIS. If we have a parameter representation where we can use multiple parameter vocabularies in similar ways that interoperate themselves, again, not choosing one or the other, but using each one of those components to extend the reach of all of the others, then we have a much more powerful way to engage with what people have written, legacy documents, things that there's no hope of anyone annotating. We can bring that back to life and fill data gaps and knowledge gaps in the system. Lastly, some more local EU projects. This one that's just kicked off. We had our kickoff meeting today, in fact. Tech Oceans is one that's really moving towards automation of ocean observing. It's led by NOC in the UK. It's again an international European project, but it also has partners around the world. And the key thing here is that, very soon, automation is the way to observe these massive geospatial and temporal gaps in the ocean. And we're going to need the machines to be pumping out data and information. And if you've hard-coded something into a machine using a particular way of serving data, it's sometimes hard to change that on the fly, especially after manufacture. That's why the actual back end, the frameworks that thing is reporting to, they themselves have to be interoperable. So developers of technologies, hard technologies, don't have to be running after the next idea that comes up in the next funding cycle. Whatever it is from a past funding cycle has to interoperate with what's coming out subsequently, if it's going to be deployed in an operational context. So it's really exciting to work, again, with technology developers and technologists who are deploying that tech, because again, those frameworks will likely survive longer than many of the component projects. So that's just a few examples, different kinds of flavors, some from digital diplomacy, some from hardware engineering, and some from getting federations of institutes to work more closely together, managing scientific output so that it's scalable and survives past funding cycles and through generations. So that's it for me, and I'll hand over then to the next presenter. I think Alison, that's you, right? Yeah, that's you. Great. Barbara, I don't know if we're doing questions at the end, I assume, right? Yeah.
You can have questions now. A few if they pop up immediately.
Okay, so a few questions now I heard, if I heard that correctly. Or not. Okay, that was background information, I suppose. Alison, you're free to share your screen. Your mic is very faint, Barbara. I can't quite hear you.
Okay. There is a question.
Mm-hmm.
Do you have a paper you can refer to?
I mean, many papers you can refer, but in what respect? So with the Ocean Info Hub, again, the Ocean Data Information System, there are some links I can provide access to, also to recordings of some of the UN Oceans meetings where we discuss this and bring together regional partners. The Tech Oceans has just started, as I said. It's available on Cordis. I'll put a link in there too. And the HDF, HMC, I'll put in links to the websites. So Zach, it'll come in the chat. Or better, it'll go into the document. How about that? It'll go into the document, so then it's there for posterity. Okay, all yours, Alison. I'll take over with the notes.
Thank you very much. I'll just share my screen. So, yes, so I'm going to speak about the outcome of task 3, which is to derive use case requirements. And I'd like to begin, first of all, by stepping back a little bit to what was presented at the last plenary session in March to explain where this came from. So between November 2019 and March 2020, IADOPT group members were invited to contribute user stories. So to describe how they're using terminologies in their own work, or indeed how they might like to use terminologies in their own work. And these were contributed as GitHub issues. And there's a link to that at the left of this slide. So those are still visible there. And at the last plenary as well, it was also described how these user stories were asked to follow a particular template, which is shown here on the right. And so I think it's always useful to give an example. So I'm going to just paraphrase one of the contributed stories here. So user story 10 was, as a biologging data curator, I want to enable interoperability of similar measurements from a range of instruments so that data from different sources can be imported into a database and queried across databases. And so this use case would cover a number of scientific domains, including animal behavior, biodiversity, and so on.
Alison, sorry, it's going here. I don't think we see your slides going through.
You can't see them?
Well, we still see your first slide, the title slide.
Well, that's strange.
You might be sharing the wrong window.
Okay.
That's possible.
Just bear with me a moment. That's not right. I'll just stop sharing for a moment to try again, see if I'm sharing the right window. Okay, is that better? Can you see?
Yeah, it looks good. Yeah.
Okay, so apologies for that then. So I just talked about the first slide, explaining the format of the user stories that were submitted to GitHub. And we had 17 of those contributed in total. And so these user stories were then analyzed and expressed in more formalized language to derive a series of use cases. And that's what's summarized here in this slide. So, for example, the user story I just quoted, which refers to semantic operability across data sources, we can describe that perhaps more formally as needing semantic alignment. And so that's use case 1.3 in this slide here. And for each use case, we also worked on a description to explain what we meant by this formal representation. So for semantic alignment, we said that that means creating mappings between terminologies using established relationships and recording and preserving those mappings. And also, as we progressed through this use case analysis, we found it was possible to group the use cases still further. So, for example, semantic alignment, terminology management, terminology search are all examples of a general use case group of terminology generation and management. It's also worth pointing out that whilst each user story could be aligned with at least one of the use cases, it might in fact be aligned with more than one. So the user story 10 example, which describes the need for interoperability across instruments and database, is an example of semantic alignment, but it also needs faceted data searches to be able to allow queries across multiple databases. So it fits into two of our use cases. And this slide just shows schematically the links that can exist between the user stories, the use cases, and the individual requirements. And there's a link at the bottom of this to show how we did this analysis using Google Docs. But I'll show you a couple of examples from that in the next slide, just to try to distill it down for you a little bit. So in effect, what we did was to prepare a large matrix listing all the use cases that we had down the left-hand side there in blue. We had a total of 15 in the end, so just a couple on this slide. And we took a note of which user stories they also corresponded to. That's the second column. And then across the top in the green, we had a full list of the user requirements. And again, as I say, this is a summary. So we actually had about 25 requirements, I think, in the end. So this is just a selection of them for illustrative purposes. And essentially, our method of working was to go through each individual requirement and mark those that corresponded to an individual use case. And it won't surprise you to know that in some of the use cases, for some of the requirements rather, they corresponded to many of the use cases. So for example, the requirement to have a terminology hosted by a reliable semantic repository was needed to satisfy 9 of the 15 use cases, whereas we only had one use case that required terminologies to provide multilingual terms. So I just wanted to show you a couple of examples of the requirements that resulted from our use case analysis. Again, at the top of the slide here, I've put a link to a file on GitHub that contains the full list of requirements that we've derived so far. But in this slide, just one example. So we have a requirement that concepts have persistent resolvable URIs. And we felt it was important not only to have, if you like, a heading or a title for the requirement, but also to give a description for each one. And that's included here as well. And this was partly to help our own conversations within the group so that we were sure that we were all talking about the same thing when we were discussing these requirements and we all understood one another. And then, of course, it's useful for presenting it to other people like this. And so we've given a couple of examples here of persistent URIs that are in use. You see also in red at the bottom as well that I've highlighted something called the FAIR semantics criteria. And this is another list of requirements that I will say a little bit more about in a moment. And here's just another example. So the requirement that terminologies should be based on simple atomic terms and that can be used to make more complex compound terms. And so that's perhaps best explained again by an example. So by an atomic term, we mean something that can be a standalone term that can be given its own scientifically meaningful definition. So flower, for example, or color, they can both have definitions in their own right, but then we can combine those atomic terms to make something else which is meaningful. So flower color or color of flower. However those are combined will follow the particular semantic rules of a terminology. And so I mentioned the FAIR requirements. So I adopt, in the end, produced 25 of these requirements based on our user cases derived initially from the user stories that were submitted to us. In March of this year, the FAIRS project published a preliminary set of recommendations about FAIR semantics, which was based on the outcome of a survey. And there's a link again to that document here. They produced a list of 27 recommendations, 17 preliminary ones and 10 recommending best practice. It's interesting to see that there is certainly some overlap between the requirements that IADOPT have produced and the FAIR semantic requirements. Some of them also come from slightly different perspectives. So for example, looking at the requirements from the perspective of a terminology provider as opposed to a terminology user. So some of them give slightly different perspectives on the same thing. But I think it's also fair to say that our analysis of the user stories has come up with some requirements that aren't yet included in the FAIR recommendations. So perhaps some of our work can feed into their next round of recommendations. So it's fair then to ask whether the terminologies that are currently in use do meet these requirements. And indeed, how can they be used to shape an inclusive semantic framework? So I'll hand over to Gwen now, unless there are any other questions about this. Gwen is going to speak to us about some of the terminologies currently in use.
Thanks, Alison. Can you stop? Yeah, stop sharing.
While that's coming up, perhaps Alison, a question. So, you know, there are many groups providing interpretations of the FAIR principles and sets of recommendations, and synthesizing those is going to be very, very interesting, you know, to see what people saw, what they agreed on and what they disagreed on. Because again, the FAIR principles are only principles. They're not prescriptions, right? So what is the intent? What is the intent in terms of how do we reconcile all of these? Is it bringing these groups together? Are they willing to do so? Or because again, in different operational realities, FAIR will be interpreted differently. So I'm just curious as to what the next step would actually be.
Well, my understanding, first of all, is that FAIR is not complete yet. So it's a project that's ongoing. And my understanding is that there'll be another iteration of the FAIR requirements. So it is possible that groups like IADOPT can feed into those requirements and recommendations. I think, and others may have other views on this, but I think the best that we can do is to come up with recommendations for best practices, and ways in which we can converge. It isn't something that we can dictate to particular semantic repositories or particular vocabulary managers, for example, but we can all look to be hopefully moving in the same direction. That's how I see things going, and having this overall semantic framework and seeing where our individual repositories or our individual vocabularies that we manage fit into that. And if we're thinking then about how to develop in the future to try and move in a general direction of convergence, that's how I see this coming. So I don't think that we're competing in any way with FAIR. I hope very much that we can converge and work together.
Mm-hmm. I hope so too. And I think in a sense, we have to be a bit, well, not us necessarily, but through our networks and through our funders, be a bit insistent on that, because it's getting quite boring, frankly, in terms of implementation, where every project interprets things somewhat differently. Or again, a set of recommendations takes people to one or the other project, use this terminology, use that terminology. It just depends on who's at the table and who happens to be on the grant. And this is getting very disruptive to system engineering. So again, this idea of a convergence point, something like a general framework, which everybody who wants to play the game can work towards, such that their products are in a marketplace that is operational and people can build stuff on, is needed, because right now it's becoming a little bit silly, frankly. Very innovative, very interesting, lots of good papers, but when you're trying to actually build something, a complete nightmare. So I'm really happy to hear that.
So anyhow, I just wanted to say that what we did, we try to align to what FAIR is doing. So anyhow, I think everything is in progress now, and we can still influence each other outputs.
Yes,
and
yes, of course.
And there is the Fair Convergence Symposium now coming up, and I think this will be also a topic of it, how we can converge these different approaches to interpret FAIR principles.
I'm sure, and I'm sure there'll be more recommendations, etc. But in the meantime, there are stakeholders that need to build something, right? So along the way, you know, thinking about a new working model where something is, if there's a new group coming up, to bring them into the fold through coordination mechanisms like RDA or so early on is really important, because some of us, you know, can't wait in terms of deploying technologies.
Right. So you can see my slide, deliverable 1. So I'm going to talk about the work we've done to gather information about existing terminologies that are currently in use in environmental research. So the first 6 months of our project, when we started our working group, we put a lot of energy in developing a survey that was addressing both users of terminologies as well as producers or maintainers of terminologies. And we gathered some information in a survey. We got about 40 responses in the first instance, with a lot of very, very detailed information, and we presented some stats about the outcome of that survey at the last RDA working group session. So here, I'm not going to repeat that, but I'm just going to show what we've done with this information. So we compiled everything, we put everything in a Google Sheet that is available through that link there, so that when you will have the slides, you'll be able to reach it, and it will be as well in our documentation, in the notes. And so at the moment, so in addition to the terminologies that were submitted to us at the time, we also gathered additional terminologies afterwards. And at the moment, we've got about 100 terminologies, and it's growing, and it's probably going to carry on growing until probably the end of our project. So this is work in progress, really, but in terms of compiling the catalog. So at the moment, we've got a broad range of, it covers a broad range of disciplines and domains within the environmental sciences, and some of them are not even directly related to the environmental sciences, but they are from close domains. And there's also a big diversity of types of terminologies, of scope, and the range of concepts they target. So basically, we've got, I think, a full representation of that spectrum of semantic artifacts that is presented on that slide, going from glossaries right up to full ontologies. So the way, so as you can imagine, it was quite difficult to actually try to analyze all that in terms of, well, we needed to be really to constrain it. And what we did, we used our the semantic model element to try, or we use our identification of the different components of what make an observable property, and looked at the number of terminologies we had that actually addressed those terms. So as you can see here, we've got over 40 terminologies that dealt with quantity kinds or had terms associated with quantity kinds of properties. We had over 45 terminologies that name or describe the target object. 14 of them were backed up by a conceptual model or a conceptual framework. 11 address method description elements. And we had 13, so one of our initial objective was to also obtain information about the nitrogen use case. So we asked terminology, people who were filling the survey, we asked them to indicate whether their terminology contained concepts related to nitrogen. It was just in order to be able to focus on one particular kind of measurement that was broad enough to encompass many kind of measurements, but at the same time focusing on one particular object or chemical element. So this is just, I mean, there's going to be a series of slides with just listing out, digesting a little bit what is in the spreadsheet. So it's a series of quite boring tables, but I think it just gives an idea, and it allows people to go back to it and have a look at, you know, those different what sits under those different categories. I have to stress that those are examples. It doesn't mean all the terminologies that meet that criteria are there. It's just a selection, and I tended to select the ones that had maybe the broader coverage. So the ones that are more narrow are in the spreadsheet, but they are not presented here in the slides. So here you've got example of terminologies which contain terms that defines properties of quantities. So obviously there is QUDT for quantity kinds, a well-known terminology for quantity kinds. Then scientific variable ontology, the CF standard names, the biodiversity parameter usage vocabulary, biodiversity thesaurus, ecosystem ontology, suite, anesthese, and anesthese. And as I say, those are just examples. Then the example of terminology which have terms that address the target object. Again, there's repetition here because obviously some terminologies address most of those components I've been talking about earlier. So here we've got, in addition to the one I mentioned before, we've got the ICIS parameters, biodiversity thesaurus, Uberon, ENVO, and then the other one I already mentioned. Then some terminologies are actually addressing phenotypes and traits. And we've got quite a lot of those coming from either LifeWatch or OBO. And some of them are very specific to particular organisms, looking at the whole series of traits. And obviously traits and phenotypes is quite particular in that it can be both a property of an object as well as being a part of the description of that object or that an identification of that object. So you can see here a series of a selection that shows, you know, the span of speciality of those vocabularies. And there's also some attempts into bringing together multiple vocabularies. And I think that's what the phenotype and trait ontology is. It was trying to bring together, or the unified phenotype ontology, try to bring together terms from multiple phenotype ontologies. So I put here the biodiversity parameter usage vocabularies because we've got, we're actually using traits a lot for defining some of our parameter codes. Then we isolated the terminologies that actually have developed or are built around the conceptual model. So, so this is just putting together multiple simple atomic concepts, as mentioned by Alison earlier, atomic concept to create more complex descriptions of observed properties. And obviously here we've got observation and measurements, which present the basis of that conceptualization. The complex property model. So those are actually, they don't provide terminologies that describes the object, but they provide the conceptual framework for it. Then the biodiversity parameter usage vocabulary uses a semantic model, and we've got anesthese, USMTR, OBOE, CF standard names, and the linked Earth ontology, all of those using conceptual models. And we will hear more about that later on. Then a few terminologies are actually also using methods as part of their description of observable properties. And here are, I think there are all of them here at the moment. It's not a selection, it's actually all those terminologies that mention, that have terms describing methods. And then finally, the examples of terminologies that have mentioned that they do have terms related to nitrogen, and those will provide us with some good example of for that particular use case to enable us to compare the different terminologies and try to see how they align. And also here I wanted to mention, we asked, one of the questions we asked as well was, what other terminology do you align your terms with? And this is just a rough extract of all the terminologies that people mentioned that they are using to align, that they are aligning their terms to. So noteworthy here, it's KB. KB for chemical substances is widely used, as well as in the marine environment, worms for marine species. And then ITIS is used as well as a reference for taxonomic names. But this is just really a snapshot, and it's not comprehensive. We will build a more comprehensive list in the course of the next few months. So the next steps really is to match those terminologies to the use cases mentioned by Alison earlier, and also to the user stories. So the use case requirements are really domain agnostic requirements, and more addressing the kind of like technical requirements that would be needed for particular user stories from a technical aspect. But then the user stories requirements themselves require content analysis. So they need particular content. They need terminologies that deal with particular content. And this is where we will develop the content requirement. So by comparing those various terminologies, we will identify gaps and identify overlaps. And this is what Maria will be talking next. So I just wanted to say the first step between the transition between what I've just presented and what Maria is going to present now is we took all the terminologies that said we're using a semantic model or a conceptual model. And we just looked at the terms they were using to identify the different components of that model. And we just listed them in that, very simple spreadsheet, and colored them according to their to what they were addressing. So like in light blue, you've got quantity, quantity kind, quality, trait. So they are really terms that address the property of the measurement or of an observation. Then a few terminology made specific reference to statistical terms. And then in green, we've got the target object. And you can see here all the different terms used for the target object. I won't go into the detail of that because Maria will address it. And then in the orange, the matrices, and then the methods. So this is just to make the transition with the next presentation. So, is there any questions, or do we just carry on?
I'm wondering if Maria can talk because I don't see her micro. Maria,
Can you hear me?
Yes, okay.
perfect.
And can you please also tell me if it goes into presentation when I click here?
Perfect.
Yes.
Can you see me? You can see me scrolling through? Okay.
Works.
Yeah.
Great. Hi, everyone. So I guess there are no questions for Gwen's presentation. Should I start? Okay.
I have one question. Sorry.
John, go ahead.
Hi, John.
Hi, Gwen. Do you think you've missed any vocabularies, that is?
Yeah, well,
it seems like you've
as I
been
say,
pretty
it's not-
thorough.
Oh, I see, right. Well, I don't know. There might be some hiding somewhere.
Yeah.
Did you spot any that we missed?
No.
No. Okay.
I think it's great. I know the amount of work that you all have put in is very, very significant, with a lot of people working on it. And it seems that it would be the authoritative reference now, unless somebody objects. That's great. Thank you.
Right. Okay. Thanks, John.
I think I'd also just append that by saying, you know, it'll always be open-ended, but the thing
Yes.
is, like, do we have enough, like a kind of rarefaction where the new ones that we get are not challenging the framework or the conceptual model? You know, that means we've reached a saturation point and found something robust enough to take on new ones, right? So it's not an open-ended task. It's just that we need enough examples and counterexamples to see if what we got is stable enough. I think that's the spirit. Gwen, what do you think?
Yeah, that's fair. That's fair to say that. But I would just, I'm just thinking all the time that we have focus. We're obviously focusing on environmental sciences because that's where most of our expertise come from. But obviously, when we go maybe on, related domains, we might find, other terminologies that might challenge our conceptual model. So I think that's where it's important to try and gather more information from those edges, just to make sure that, what we build is truly interoperable.
Yeah, that's an interesting point. You can easily, it's a very smooth transition from environmental to ecological to biological and to medical. And so it actually would be an interesting validation test to at some point jump over into the medical and say, does the model work there too? But that might be downstream.
Yeah,
yes,
it could be downstream, but also from like previous work with Tadwig and other, for trait-based parameters and things. I think it will still work based on my pre-exposure to that community. Of course, there'll always be a counterexample, but I think it's getting close. But as you see, like, there's still work to do on this conceptual model, because some of those slots are, again, indeed fuzzy, but that's where we need this number of examples to be able to actually articulate what they are in a bottom-up way, Aristotelian, as opposed to sort of dictated.
This is what we want to do also in the discussion session, to collect some further examples. But let's go on with the next presentation, if possible. Maria?
Okay, great. So yes, as everyone has hinted prior to this part of the presentation, I'm going to be talking about the ongoing work towards the outcome of task 4, which is to analyze semantic representations of observable properties against the requirements. And what I'll be talking about here is specifically the conceptual requirements, so not the technical requirements, such as does a concept have an IRI? And so just broadly, the purpose and objectives of the activity falling under this task is to find the commonalities and the differences among the cataloged community preferred top level ontologies and semantic models. And just to clarify here, we're talking about the domain independent top level categories. So things that are not dependent on the terminology of a particular domain. And we also want to look at determining the degree to which atomization is necessary to enable accurate alignment of concepts across terminologies. And atomization, this goes back to the requirement that Allison mentioned in her presentation about what is the smallest basic unit that has a scientifically meaningful definition, and that we would need in order to describe these variables that we're working with. Lastly, we also want to identify gaps or any critical differences in the expressivity of these top-level ontologies that may hinder interoperability among them. And so the analysis steps that we took to approach completing this task were first to determine the primary top-level categories used in each of the cataloged ontologies and semantic models. And again, some of the terminologies use the same top-level ontology. For example, there are multiple ontologies that use BFO, basic formal ontology, as their top-level ontology. The second step was to, once we've identified these top-level categories that we need to express our variables, to cluster them together, so to generate a complete set of unique top-level categories that encompass all of the necessary top-level concepts that we need. And then to generate definitions and examples for each of these unique categories. And lastly, to look at the nitrogen variable examples that we had previously collected, to attempt to atomize them and categorize their components according to these categories that we determined in step 3. So the first step, just going in a little bit more detail, is to determine these top-level domain-independent categories by looking at what I guess I could call a reduced model of each. So here you can see our BFO model is actually very simple, but that's just because we extracted only the top-level categories and relations that are relevant to the variables that we're looking at. Yeah, here I'm just showing some snapshots of relevant concepts in the complex properties model, O&M, observation and measurements, OBOE, and SVO, the scientific variables ontology. And so in this step, we're just looking at the top level categories. You can see, if I go back here, you can see that this isn't just about the top level categories, it's also about how they're connected to each other. But for the first step, we're just looking at the top level categories. So the first step is to cluster these categories together across the different top level ontologies and determine, which ones are approximately the same and refer to the same ideas, top level ideas. Again, generate this unique complete set of categories that we need for variable expression. In the third step, we wanted to generate a set, generate definitions and a set of examples for each of these top level groups. And so to this point, we have refrained from giving any of these categories a specific name. As you can see here, we have assigned them what we call provisional letter code, so A, B, C, D, and E. And we have associated keywords with them, so top level terms that might be associated with this category, but we haven't honed in on a specific name for each of these. And so you can see that the top 5 core categories that we came up with fall into 3 main types. So the first type is with respect to what is being measured. And we're looking at, I'm going to start by looking at categories C and D. So category C is the target object that is being observed, and this is the independent object that we're looking at during an observation. And the definition that we've derived at this point is that this is any biological organism, chemical, meaning substance, or physical or chemical phenomenon that is being observed. And examples for this would be wave, a mechanical wave or an electromagnetic wave, wind, carbon dioxide, or even a polar bear. Secondly, we have category D, which is the matrix or the substrate, and this falls under what we call the where theme. So this is the environment in which the measurement is taken. And examples of this might be sediment, water, atmosphere, or soil. Then we want to look at the characteristic of the target object. And in different ontologies, this might be referred to as a quantity, quantity kind, quality, or trait. And the definition that we came up with for this was that it describes a measurable or qualifiable characteristic of C, meaning the target object. If it is measured, it also determines the dimension of what is being observed. And examples of this would be a period concentration, such as a mass concentration or molar concentration, count, color, or abundance. Lastly, we have these categories provisional code B and provisional code E that are related to how, well, so B is sort of how and also what. So B is category where we perform some kind of post-processing of the observation. So it refers to processes of modifying A, which is the quantity or the quality. And examples of this would be a standard deviation, annual mean, or computing a standard error. Lastly, we have provisional code E, which refers to method-related terminology. And this is related to how we perform a specific observation or simulation or computation. And the definition we have for this is the procedure used to obtain a value for the combination of A and C. So in order to obtain a value, you can't just have C or just have A, you have to have a combination of these two. Lastly, we have this a sort of catch-all category F, which we've referred to as constraint for now, and defined as a condition in which C is at the time of the observation. So from the examples, I believe the first one is from CF standard names, I think. And it's long wave radiation assuming clear sky. So clear sky, that would be an environmental condition for the measurement, or dissolved, which might be the state of a target object with respect to, let's say, the medium that it's found in. And step 4 and subsequently step 5 are going to kind of transition into the working session that Barbara is going to be leading in just a minute. So the next step was to look at our nitrogen related variables, break them up into atomistic components, and try to categorize each component according to our general top level groupings generated that we just discussed in the previous slide. So here you can see we have some examples of a few variables that were very straightforward. Nitrogen per unit sediment mass, where you can clearly see what the target object, the matrix, and the quantity is. Same thing with filtered water total nitrogen mass concentration. However, of course, step 5, which I did not mention in the beginning, but it should have been anticipated, is that at this point we will identify patterns that cannot be adequately expressed with just the top level chosen categories that we previously described. They might require other categories or perhaps a more complex composition. So for example, with this variable that indicates a ratio of 2 fluxes, it has 2 target objects. How do you go about expressing this? And so I'll hand it off to Barbara at this point.
Thank you very much. Can you stop presenting so I can share my screen? Okay. Can you see my screen?
Yes.
Yes.
And can you hear me well? Because
Yes.
yes. Okay. So now we have less than 40 minutes. It's only half an hour. I try to keep short my introduction to the discussion. I think we got a quite good overview what we has achieved so far. I would like just to give you a brief introduction into the models that we analyzed, and also the terminologies for describing nitrogen concentration, just as an example. And after that, I would like to ask you some questions where you could help us in continuing this work. So first, I will show you on Padlet. That's a nice tool, a collaborative tool. Although today we don't work together. I just show you how I have tried to connect to that what has already been presented by my colleagues. So we have here an overview of the data models that we could find in our catalog, starting from ONM and all the ontologies that build upon ONM, like SOSA and SSN, and also a complex properties model that extends the ONM approach. Seronto, an ontology where I was involved 10 years ago, the SVO, the scientific variable ontology, the Oboe and the Bafo ontology, just to mention a few. So it's not comprehensive, this list. We just started. And here as columns, I could say you see the model overview as figures. Then the C, the A, the B, the F, and the D, and the E atoms described by Maria. So I introduced also the propositions here. What, where, I think it's what, where, and how. And some names, labels for them, just to make it more concrete. We won't fix ourselves now to these names, but I think it helps to have also this here. The target object, the quantity, quality, kind, and the statistical concept, constraint, and this matrix, substrate, and the unit of value and the method. And all in the same color, and I tried to make these metrics to show how this would look like if you break it down to the different models. Yeah, and something that really is interesting to find out is the observation and measurement approach. We all know that we all use this ONM approach, but in our case, for describing observable properties, we we are at a too broad level, and it is not specified how this can be done in a unique way or in a machine readable way, because the phenomenon type of observational measurement that we see here, the phenomenon type, is could be defined as by us as we interpret it. It is a mix between C and A, but it is not possible to atomize this. And so it is for SSN, for the SSNO ontology or the SOSA ontology, which both build upon it, although it leaves it open how we define this. It could be just a quantity, but it could also a mix between target object and quantity. It is the complex property model, CPM model, that brings up this issue and tries to disambiguate these two terms and has an object of interest and an observable property as two separate concepts, but introduces also statistical measure, constraints, matrix, and unit of measure. And Seronto does it similarly. It has an investigation item and the parameter. And it has another investigation item to specify the where, so the matrix, and addresses also the parameter and method as a combination to then come to the method concept. The SVO, it is also an approach to describe the phenomenon and the property as separate concepts, and has then phenomenon, property, and an operator to describe the statistical concept, and process for the method. Oboe is also mentioned here. It has the entity and the characteristics as for the property, although I'm not totally sure, but I have seen that it has been used also as a mixed concept between target object and quantity, but also as a specific atomized concept for property. And it has protocol for method. And Bafo, here we can identify material, entity, and quality. And the qualities are sometimes also mixed. This is what I could find out so far. And if you go to the nitrogen example, you see here we are talking, for example, for the dissolved organic nitrogen, and by means of a method. Okay, this you see here that the different terminologies use different labels for addressing more or less the same thing, and they have sometimes a combined parameter, a combined observable property concept, but also sometimes organic or how do I say, atomized elements for describing this concept, this observable property. For example, ENFDES has both, has a combined term, and it allows also to atomize this description into organic nitrogen concentration as a constraint dissolved, and sediment as metrics. And so it is also for BODC and NERC vocabulary. You will find organic nitrogen concentration, sediment, and also the unit. What you can see that both are built upon the CPM model. So it's clear that they try to atomize in the same way. The SVO has also atomic descriptions for nitrogen atomic, count per mass concentration as the quantity, kind sediment. OBOE, yeah, we have here from the ANAE interpretation of OBOE, it is atomized in target objects and mass concentration. But I have seen that this is also mixed sometimes. And the other ones here mentioned are using composed descriptions in one label. So I see here two problems. I see here that the labels are not identical, so it's not easy to find automatically what is meant here. And yeah, it is not always easy to map one to the other if they don't have atomized elements. So what I wanted to show here is that there are different ways to describe the same thing, and this makes it not easy to reuse these annotations. And then also the data that is annotated with these terminologies. And we will have to find out a way how to map one to each other, but this is the first step to each. So going back to the discussion slide here, I would like to invite you to help us collect challenging complex property examples, because simple properties are rather easy to map to each other, but the more complex a property becomes, the more challenging it will be for us to map one to each other. The next question is, are you willing to join the framework development team? And the third would be, would you be interested to test the framework with your own data? Yeah. So please use the collaborative notes if you are interested to join. But now I give you a Padlet where you could put your first ideas for challenging complex properties examples. And I put this link in the chat. And I open the discussion now. You can enter just by clicking on the plus button here, which I don't see at the moment, because I have too many. So yeah, here you can just type in, and here's a plus button, and you can just enter your ideas. So,
Barbara, can you maybe specify what is it you want people to? I mean, at what kind of? Is it at the concept level, or is it examples?
No,
you want them
just,
to?
like we had this for the nitrogen observable properties. These types of information, which are really getting challenging for us to identify how these could be mapped one to each other. So the concentration of organic nitrogen is okay, but if it becomes more complex, we introduce more target objects or context objects that we have to include. Then.
So you want people to add some examples of complex properties. Yeah. Okay. Thanks.
Barbara, could you go back to the previous one for a second? So you have created a grouping, the lettered groupings at the top level. Is that anything more than a temporary grouping of convenience to think about similar things together? It's not a target grouping in any sense, is it?
These are the smallest atoms that we could find out. We label them correctly at the moment, because it's not about finding the right label, but to identify these pieces of information.
So these things are hard for me to talk about, so sorry if this is obscure. But the item C in particular nags at me because I'm so used to the phenomenon approaches that O&M captures. And in C, it seems to me we've clearly lumped one kind of target object, which is a physical thing. Sorry, a concrete physical thing. I don't have the right words, with another kind that is a evolving physical thing so let me say that a little differently. It's not a primary observation. I can make a primary observation of a person, but I can't make a primary observation of a wave. I have to measure it through intermediate things and then convert it, right? So when we talk about those being atomic, I think it's easy for some of us to see smaller pieces, and I'm wondering how the distinction is made about what you lump and what you split.
I think it's object or phenomenon, John. It's just at the moment where the terminology we're using is it's temporary. So that's why Maria said we are using keywords rather than, and that's an interesting input you're bringing here, because obviously each of us will see
examples we'll have our own categories
that don't fit the terminology, but they still all fit the object of the observation. So the wave is still the object of the observation, the surface wave, but it's a phenomenon. It's not a physical object.
Oh, okay. Let me ask the question.
It's not a feature of interest. Yeah, it's not a feature of interest. Not that what has a X and Y coordinate. It's an abstract concept of something.
Yeah, I still struggle with that particular one, but that's okay. Let me ask the question with a much more concrete proposition. About, I don't know, 7, 8, 10 years ago, I took CF, a long time ago, forever ago, I took CF and analyzed all the terms and broke them down into all their pieces that I could find and stuck labels on them. And so I managed to dig up that document while you're talking, and I have that. And I don't, probably the easiest way to deal with it is just throw it over the fence and let you guys do with it what you will. But if there were some particular way you wanted me to present that collection of categories, if you like, I could do that. It's pretty self-explanatory. It's just a list of columns. Each column has a header, all the different concepts in CF at the time under that column, like element is a column and living matter is a column and medium realm is a column and so forth.
Yeah, so we would be very happy if you could
just throw you the whole thing.
Mm-hmm. Yeah, but I think this pertains also to the point I put in the chat.
Yes,
that it's tricky here because when you're looking at things like Buffo, that's really high up, and a lot of the things that are in, let's say, more mid-level terminologies like the SPO, BODC, OBOE, that's already much closer to parameters than Buffo would ever be because it's scoped very differently. We'd have to bring in the OBO ontologies that plug into Buffo and meet at the same semantic level as these other examples to sort of normalize this space out. And I think that's where, John, the issue shows up in this case with your system, right? Because you have to crosswalk between these major gaps in specificity and generality.
Yes, I think so. But also it is, I think some of the weird CF cases are good examples of sort of slicing in between different columns and or just things that hadn't surfaced yet. And so it's yeah. What you said.
I think this also comes from things like, so Barbara, you switched over to those examples, like put in a few into the pad, exactly. So like those are some from, let's say, weather monitoring or any kind of flux measurements. And these are like second order derived parameters. They're not like simple measurements of an object of interest. The object of interest was a while ago, and then things happened to come up with these sort of parameters. So I think also with this building on the IADOPT work that's happened now, we've actually detected where now we have to kind of build out these categories in like 3 dimensions, so to speak, to separate out the granularity that comes from the parameters and the derivation of new parameters from more concretely grounded ones in the physical world, and then the abstraction layers across the different resources. It's a complex task, and it's really great that we actually have a shape of it through the existing work that's happened. But I think now that's the phase 2, so to speak, a little bit more conceptually challenging.
Yeah, and I must say, we have just started this. Okay, we are at the beginning. And, so it's that's not our final work. So we.
And I think
it's not a criticism. Quite the contrary. We have a shape of this now, which is very useful.
But I think awesome. I like your analogy of the 3D of the three-dimensional, because it's really, you know, we need to identify each of the resources have got their role to play, but they are at different level of a different location in the world model, and it's identifying the niche that they occupy.
Exactly. Like we have one axis, which is like the semantic ladder that was presented, you know, is what's the expressivity? That's one dimension. Another one is how abstract or concrete is it? So that's the derivation scale. And then the other would probably be controlled by the domain. I'm not sure, but it'll be exciting to find out.
Right.
I think another issue is that the same, so what if we look at this, the C, so the target object, or the object of interest, or however it is called, can have different roles here. Yeah, it can be one time a matrix, and then the next time the real target object. So we will have also to deal with different predicates. At the end, we need a conceptual model, not only with concepts, but also with predicates to capture this.
Yeah, it seems like the right time for this document that's been lurking in the back of my shelf for a decade or so.
I think so. I think that's important to bring that up to light again, because again, like some of those international initiatives that I described in it will go this way, not knowing what they're about to hit, you know, the complexity they're about to hit. So even at this stage, IADOPT could say, watch out, you know, you're entering Wonderland here. This is a rabbit hole. Decide early how you'd like to scope your work or be lost to the depths of despair.
So if I come to my questions, can you help collecting challenging complex property examples? We will provide a GitHub repository for this. At the moment, it was just to launch this task. But I think it's very good to have a list of different complexity here, also coming from different subdomains. You know, biodiversity questions have completely different issues than properties, including chemical elements and so on. And also if it comes up with modeling variables or so, then we have, again, different problems to address. And John offers, yeah, that's perfect, that he will present this also the next time. One of our next sessions, or not only sessions, working teleconferences would be also fun.
Make me laugh, yeah.
If you can, if you would see you after a year.
Does it actually sit in a spreadsheet, John, or is it just
it's the final form is there's a raw spreadsheet and there's a final spreadsheet, and yeah, Lord knows how meaningful it is now, but it was pretty thorough at the time. I just couldn't figure out what to do with it after I did it.
Point of order. So Marcus, you have a question in the chat. Would you like to vocally speak that, or I can also read it out? Up to you.
Hi everybody, here's Marcus. Yeah, sometimes I have background noise here, so I never know when I can speak. Yeah, thanks for the detailed and important work. I wondered whether you have thought about cross-linking also to the IOPAC Gold Book, which in the terms of nitrogen, which is a chemical species, is, so to say, the gold standard glossary in chemistry. It's human readable, but it's also, I mean, it has an API. I can provide the link here if you want.
Yeah, that's good.
Yeah,
So
we've been linking to it, but Marcus, do they actually have terms for chemical substances? I don't remember seeing like terms for, you know, nitrogen or carbon, or I might be wrong. I know we're using it for as a reference for particular properties, chemical properties.
I'm pretty sure nitrogen is in there. I mean,
Okay.
it's
Right.
many hundred pages printed. So
thank you for mentioning it. We were not at this stage yet, but we will come to this for sure. So there are so many things to elaborate and to analyze, but yeah, thank you for pointing this out. Yeah, we are approaching already the end of the session. So I know we are also not that many, and many who are here are already part of iAdopt. So I hope that you still continue to help us with examples. And if you are not yet an iAdopt member, please go to our website. Here, our website at RDA. You can join us here and the members, and you can then participate at our bi-monthly teleconferences each first Thursday at 6 p.m. Central European Time, and each third Tuesday at 9 o'clock in the morning. I would be happy to welcome you there. Gwen, would you like to say something last minute?
Yeah, I was just going to put. Did you put the link to the wiki?
It is everything here on the top of the page.
It's in the document. All right. Okay. Yeah. It's just because the wiki iAdopt in a nutshell contains everything that you need to know in order.
And we have a GitHub repository here, and
yeah. Well, I just wanted to say, you know, if for, you know, anything that's been mentioned during this session, really, you know, any comments, please use either GitHub or email us. You know, if you've seen anything that, you know, you don't either agree with, or you find we are on the wrong track, or on the right track for that being, you know, just let us know, because it is a lot of work. It's a lot of investment, but it's very worthwhile, because there is a lot of work has already been done in the past, and I think we are at a crucial time where, you know, unless we work together, there is a risk of more and more overlapping resources and waste. I mean, they are very time-consuming terminology to maintain. And they are seriously needed now. A lot of people are, you know, want this kind of terminology. So there is pressure for always creating new ones, but, you know, it is very important to use existing resources and to identify, like what we're doing, to identify those commonalities, so that even as Pierre mentioned in his introduction, even if for reasons of speed or practicality or funding, you need to create a new terminology, then there's, you know, it at a minimum, it is aligned with everybody else, basically.
Exactly. And also that has the potential to be folded into something else if you can't maintain it anymore, you know, because in a sense, it's a destructive activity to generate something that you don't know whether well, nobody really knows if you can maintain it, but you have to have an obsolescence strategy so that it continues somehow, and not just hope that it does while trying to get users, because that really starts to degrade faith, not just in the product you develop, but in semantics in general. People will start to walk away from it because, you know, it doesn't work. But it does, and it can, if we work together in this endeavor. So it's quite important.
Yeah, that's a good point, and it's true as well for the user. I mean, they are expensive to maintain, but also for the user, it's actually expensive to you have to put a lot of resource to actually use semantic. So you have to be sure that actually they will be long lasting.
Exactly.
worthwhile investment, basically.
And, you know, as I see Ruth on this call, also in our ESIP semantic harmonization cluster, where we are trying to map ontologies to one another, it's hard work and it takes expertise, it takes focus, and so there's an attitude that's, oh yeah, we can just map it later, you know, so with some simple label matching. But as we've seen from this, the labels don't necessarily point you where you want to go. So it has to be aligned early from inception, if not reused right away. And I think this group and also the semantic harmonization cluster and ESIP and others can keep making this point to the larger community. Developing something locally in a silo and trying to map later is expensive and it will hurt. It's a debt, you're incurring debt. So collaboration initially, it's a bit tough sometimes, it's confusing, but it saves so much pain down the road that it's totally worth it. And when we get to see each other, we can drink together, which is even more fun.
And then just one last word. I think next session we will have a framework for discussion. And once this is agreed, then we will work on mapping one terminology, the terminologies to this framework, and we will help doing this. So this is what we are planning to do in the next 6 to 8 months.
Mm-hmm. That's interesting. So perhaps that's something that we can link as a sort of joint project with the semantic harmonization cluster at ESIP, because it has marine data themes, environmental vocabularies, and it could be a co-sponsored activity, RDA and ESIP. That would be cool.
Yeah, yesterday or this night at 1 o'clock, I was at the ESIP session, and I mentioned IADOP there. So we should really keep close contact here and know what we are doing from each other.
The good news is we're getting to know each other really well from being on all these calls.
Yeah.
Well, hopefully we'll get to meet each other again in
Edinburgh. Sure. World tour.
Okay, thank you very much.
Okay, well, thank you very much. Yes, it's been a great session.
Thanks all. Ciao, ciao.
Thank you, Pierre. And
ciao.
thank you.
Bye, everybody.
All right.
Thank you. Bye-bye.
So we will update the document. Yeah. Bye. Bye.
Thank you, and bye-bye.